This is question 2 on the 2017 AP free response set of questions. Now it gives you two Lewis structures to start off. There's less reading for this one. All right. And it says two possible electron diagrams are as follows. Explain why the diagram left is a better represent. Okay, justify. So this means you have to assign formal charges. To some degree, in this particular case, what you're seeing is atoms not doing things that give them formal charges of 0. So in the first diagram, you see hydrogen and carbon, hydrogen making one bond like it likes. You see the carbon making 4 bonds, but you also see the nitrogen making 4 bonds. Since nitrogen is not making 3 bonds and oxygen is not making 2 bonds, you know the formal charges on those guys are not going to be 0. Again, the groups, remember, if group 16 makes 2 bonds, that means its formal charge is 0. If group 15 makes 3 bonds, its formal charge is 0, right? So that helps you. And the second diagram on the right, the oxygen is going to have a formal charge of 0 because it's making 2 bonds. It's group 16. The nitrogen is not going to have the right formal charge, nor is the carbon. All right. Remember, you want the lowest number possible formal charges, and the most electronegative atoms should get a negative formal charge, and they should all add up to the overall charge, which is 0. So if your formal charges don't add to 0, you made a mistake. All right. Then it shows you what looks like a double arrow and something that's feeling like equilibrium. So I'm going to check that now. As soon as I see this double arrow, I'm thinking, maybe an equilibrium question, right? Using those dot diagram, show them. Oh, nope, it's not. I was wrong. They want delta H. Remember, count the bonds. Count the bonds. Be careful with your math. Everybody was getting those things wrong on the test, but it was more complicated. This one should be easier. You should be able to handle it. Remember, when bonds are broken, right? The bonds here are broken. That's endothermic. The bonds here are formed, and bonds formed are always going to be exothermic. That means you're going to have a negative delta H to them. All right. Student claims delta S is close to 0. Okay, this will not be on the AP, so I'm just going to give you the answer to this. The reason why is because you're going from 1 mole of a gas to 1 mole of a gas. So the number of moles of gas on both sides, and they're similar molecules, okay, and their structure would indicate that essentially there's no change in entropy. Which species is present in higher concentration at equilibrium 298? Justify your answer. Again, this is something that should not be on this test, so I will just explain it to you. Okay, once you get the delta H for this thing, which you'll look up, if your delta H ends up being a negative value, that means that since delta S is about 0, remember it's delta G equals delta H minus T delta S. If this whole thing is 0, basically, then if delta H is negative, then the forward reaction is thermodynamically favorable. You're going to end up with more product. So if delta H is negative, then you're going to get the K value is going to be large because you're going to have lots of product. If your delta H is positive, then it's going to favor the reverse direction, which means when you do your products over reactants, you're going to have a lot more reactants. And so in that case, the K value would be small. Again, I don't think either one of these are fair game. However, I thought I should go over it since it was in the question. All right, so if I was to answer, I'd say, now I don't know what your answer is, but if your answer is negative, say the reaction as written is thermodynamically favorable because the delta H is negative and the T delta S part of the equation is 0. So delta G is definitely negative. It's thermodynamically favorable. It's going to at equilibrium there will be more product. If it's not thermodynamically favorable at equilibrium, there will be more reactant, and that affects the value of K. All right, this is how it's going to be because some things are not going to be part of the curriculum. Now, see another double arrow. I'm figuring now we're probably going to get to an equilibrium situation. So let's turn the page and take a look at that. All right, there's our equilibrium. It says, oh, wrong again. Wow. A student studied the decomposition. You know why? Because as soon as I saw this graph, I thought to myself, this is about kinetics. Now, quick reminder, there's either 0th order, first, or second. All right, 0th order, it goes down like this. Concentration does not affect the rate, so you have a straight line. These two both give you a curve, but this one looks like half-life. So you can check to see if it's first order or second order. So explain how, so the student comes up with this rate law right here. Now, for those who don't remember, they're saying the coefficient of this thing is 1. I'm going back to the equation. There's clearly just one reactant here, all right? And they're saying the rate law is this to the first power, which means they're saying it's first order with respect to the change in the concentration of that. So the question is it first order? So you're supposed to explain how the data supports the law. So if it is first order, you should be able to find a regular half-life. I'm not going to show you how to do that, but you're going to have to justify that. And so you're going to justify that by using numbers from the graph, right? So does this have, if it doesn't, and it doesn't say it doesn't support, it says it definitely does. Explain how it supports. So it's definitely first order. How does the graph justify that? All right, or the data table. You can definitely use the data table. I think actually the data table is actually easier to use in this case. Using the proposed rate law and students' results, determine the value of the rate constant K. Remember, once you have a rate law, okay, uh, once you have a rate law, you like to go K equals, rate equals K times the concentration. You can use any concentration, okay, and any rate. So you can use any row in this chart, and you should get the same value. And you plug it in to solve for K. That should be really easy. Okay, student learns that the decomposition reaction was run in a solution at pH of 13. Briefly describe an experiment, including the initial concentrations that you would change, the data you would gather to determine whether the rate depends on the concentration of hydroxides. I don't think this one would either also be on your exam because it deals with pH and the acid base unit is no longer on the exam. Again, I'll talk to you about I would basically produce a series of buffer solutions at a variety of pHs, including some which had pHs of 10, 9, 10, 11, 12, and 13 and such, and see if, as I change the pH and maintain stable pH using a buffer, whether or not the rate is actually affected. And I measure the concentration of the reactant with respect to time. That's it for this one.